I'm going to be talking about a concurrency library that I'm working on, which is based on joint calculus. Joint calculus is actually a programming language. Maybe you are familiar with lambda calculus. So it's not really calculus in the mathematical sense, it's a programming language. And it's a language that's suitable for concurrent and parallel computation. However, I would like to ask if anyone has heard of it before this talk. 1, 2, 3. Yes. I would say mostly unknown in the software engineering community. Although we know that concurrent programming is not easy and we would like to have better declarative formalisms or programming languages for it. Just to summarize why it's not easy, usually it's implemented using primitives like callbacks, threads, semaphores. All these primitives are difficult to use. It's easy to make a mistake, especially when you use shared mutable state. And it's hard to test this code also, because every time you run the program, the result is different. There are race conditions, there are deadlocks. So people usually try to avoid all these problems by going to declarative approaches, which are several, such as, for instance, using Spark, where you have parallel collections, using futures, or using streaming paradigms, or software transactional memory, or actors. All these approaches are declarative in one way or another, but not all of them are equally powerful. So actors is perhaps the most powerful of all the previous ones. Joint calculus can be seen, as I will show, as a development of actors that makes it even easier to use. A typical example of a problem that you want to solve in a concurrent application is the so-called dining philosophers problem. How many of you are familiar with the dining philosophers problem? A lot of you, yes. So the philosophers sit around the round table, and between each of the philosophers there's a fork. In order to eat, you need 2 forks. So philosophers start eating at random, and then they stop at random. You need to simulate this process, taking care that there are no deadlocks. So an example of deadlock here would be if each philosopher takes a fork and waits for the other fork, but that fork never gets free because the other philosopher is also waiting. So Rosetta Code is a website where you can find solutions for this problem in many programming languages. I'll show you a solution in C# just to see what it is like. I'm sure you understand this code immediately. Okay, I don't, so I'm going back. It's hard to use ordinary paradigms. So in my talk I will explain the paradigm of joint calculus, or as I call it, the chemical machine paradigm. Chymyst is a library I'm working on, which implements this paradigm as an embedded domain-specific language in Scala. I will also give you some motivations and metaphors to help you understand this paradigm and to see how it is, in some sense, an evolution of the actor model. And I'll show you some examples and demos. I will not talk about other declarative concurrency paradigms, but let me just mention them. So pi calculus, It's similar to joint calculus, it's just lower level. Actor model. How many of you are familiar with actor model? ACA? Okay. So that's something that today most Scala developers know. The communicating sequential processes is a formalism that was used to design the Go language, and STM is standard in Haskell. Just to mention, so joint calculus is of the same power as pi calculus and actors and CSP. I'm not sure about STM, but probably not. But probably STM is weaker. I'm not sure. So how do we approach joint calculus? Well, I can promise you that it's easier to reason about than other concurrency paradigms. But how to reason about it? I can say, well, this has no threads. You don't reason about threads. You don't reason about locks. You don't reason about semaphores. But it's actors, but imagine that you don't need to start actors yourself. They're automatically started. They're type safe, and they can take multiple messages at once. So this is not enough to understand the paradigm. And I do not recommend looking at the Wikipedia page for joint calculus. You will not understand anything. And I don't either. Instead, I suggest metaphors for joint calculus. One is concurrent functions that compute with concurrent data. This is kind of vague. Another metaphor is it's chemistry. It's a chemical soup with molecules and reactions. So let me begin with the first metaphor. What would it mean for us if we were able to make ordinary computations concurrent? Well, in a functional language or functional programming, computations means you have functions with arguments or functions that consume data and return new data. And we would like several of these functions to work on their data at once. That would be concurrency. And also, because in pure functional programming, we don't mutate anything, then it kind of follows naturally that concurrently running functions should work on separate pieces of data, not on the same piece of data. There shouldn't be any shared state. So imagine that we create special sites where these concurrent data and functions are stored. And concurrent functions can consume any pieces of data from this site. And when a result is computed, it is emitted back to the site. So that is kind of concurrent world or concurrent site where computations happen, concurrent computations happen. So then if we were to implement this, then concurrent functions will automatically begin their computations whenever their data is available. The data should be labeled somehow for them to start. And so that is the basic idea of joint calculus. Now, to make it a little more concrete, I would like to present the chemical analogy or metaphor. Now, in real chemistry, we have molecules that react, and we write reactions like this. So there's a molecule of hydrochloric acid that is reacting with sodium hydroxide. And then we write an arrow, so we say one molecule plus another molecule, then write an arrow, and then salt plus water. So that is the way we write chemical reactions. Now, let's do an analogous thing. And instead of real chemistry, we just consider abstract chemistry, where molecules are arbitrary, we define them arbitrarily, and chemical laws are also defined arbitrarily. So for example, programmer can define molecules A, B, C, and these two laws, that A plus B goes to A, and A plus C goes to nothing. Now this of course cannot happen in real chemistry, but this is abstract virtual chemistry. We have no restrictions. we can write whatever laws are necessary for our application. So imagine that we have implemented a simulator for this kind of chemistry. So we have commands to emit molecules into the soup. We have a program, which is these laws, and then the runtime system will start evolving. So it will find, let's say we emit 500 A's and 300 B's and whatever. So this runtime system will evolve this soup, finding pairs of A and B that can react and emit new products of reaction every time and concurrently. So any molecules in real life that meet, they start reacting concurrently with any other molecules. We want to do the same. That's how we want to do concurrency. Now, suppose we implemented this simulator. Now, this is not enough to actually do useful computation. To do that, let's say that each molecule carries a value now. So not just molecule A, but a molecule A carrying a value X. Molecule B carrying a value Y. Molecule here, the reaction needs to put a value onto the product of reaction. So there must be some Z here on top of A. And so the reaction is a function that computes Z using X and Y as arguments. So that's how we are going to use the chemical simulator to perform actual computation. Here is the code I'm writing in the syntax of Chymyst, of the library that I will present, which implements this computation. So there are two reactions. Reactions are written as partial functions using this Go macro. So basically you just write it almost as purely declaratively the chemical law. A plus B goes into A. Now these computations are necessary because we want to put a new value Z onto the new molecule, and so you write them in line as a function, right, like this. The second reaction takes A and C. Now C here does not have a value, it has an empty value. We model this with a unit type. So C has a unit type. Now each molecule A, B, C, and so on will be statically typed. So the type of value is fixed. Let's say C has unit type and A has some, let's say, integer type, X. So then this reaction will just print this X and emit no molecules as a result. So this is an example of programming in joint calculus. So actually, I have described everything. That's it. Yes?
So Go is emitting, I guess, an implicit function. And I guess you're passing into site a collection of firearms to this implicit essentially. The matching happens by the compiler.
So the question is, does Go pass in a function or implicit function into the site? And how does the compiler run this expression or run this this call? So each line, each expression that starts with Go is a reaction. So Go is an expression. So Go is a macro that produces a reaction out of this partial function here. So site is a function that takes a variable number of reactions. Now, basically, this declares this virtual concurrency site on which the concurrent data will live, and the concurrent functions will be there available to start processing the data. Here I declare and activate this site at the same time. In principle, I'll show you later how this works. I could declare first the reactions, so I could just say val x equals go, and then I could say site of x. I don't have to do it in line. So in this paradigm, programs are first a declaration of molecules and chemical laws, and second, a declaration of what initial molecules are present in the soup. So that's how we have to formulate our computation. So once we somehow come up with this description, we just start it and it just runs. There's no command to start, it's all declared, yes.
You only output one molecule?
The question was whether I only output one molecule. No, I can output as many as I want. I can output unlimited number of them. Here's the first example. We want to have a counter that we decrement and increment concurrently in a thread-safe manner. We design this with three molecules: counter, decrement, and increment. And the reactions are in the chemical notation like this. The counter carries an integer value n, decrement and increment carry unit values. Counter reacts with decrement and emits a counter with modified value, similarly with increment. Now, the operational semantics is such that when the reaction starts, it atomically consumes all input molecules. Then there is a computation, and then it emits output molecules. Initial molecules, we say it's counter with value 0. So now you see how this works. We can emit, decrement, and increment concurrently. And every time, the counter molecule will be first consumed and then emitted again. There is no danger of a race condition. If I emit 5 decrement and 5 increment molecules at the same time, they will react one by one. There's no mutable state here. The data stays on the molecules, so the molecule is immutable, data is immutable, and yet we implement mutation in some way, like a counter. Okay, so here's what we write in the library, in the Chymyst library. First, we need to declare the molecules. So these actually are called emitters. These are functions that emit molecules into the soup. And these are types, so you have to declare what type they have. So counter has integer type of its value. Decrement and increment are unit. Now we can declare reactions like this. Pattern match. These are actually pattern match expressions, and you can use arbitrary Scala partial functions with pattern match expressions. Anything you want. Case classes. You can use if here if you want. Anything you want. It's just unrestricted Scala code. And then you activate the reaction site. So we can also define reactions inline inside the reaction site, or we can define it in this way. So then we write it, we do it like this. This will be a non-blocking side effect of emitting a molecule counter with value 10. These are non-blocking side effects of emitting molecules increment with unit value. And then at some point, for example, the state of the soup could be that it has these 3 molecules. Later, immediately, it will start reacting, of course, to increment. Yes?
The plus in your partial function definition is special, right? Because it doesn't mean add.
No, it's the chemical plus. It actually means and, but I like the chemical notation. Yes, so this is a special syntax. This is really just syntax. All right. So if you remember the concurrent data metaphor, then emitting molecule with value is like lifting the data into the concurrent world, where it starts floating around and ready to be consumed. And define reaction means you lift a function into the concurrent world. And then the reaction site is this container where you have accumulated some data items and functions are ready to start computing with them. And function consumes input and returns output like a chemical reaction consumes its input molecules and returns its output molecules. So that's how these metaphors work. So what remains is one feature that I'm going to talk about right now is blocking molecules, which is a very useful feature but not necessary for programming, because we usually would write non-blocking code. But if you need, well, at the end you need some blocking code in some place of your code, so you have that. And after that I'll be showing actual code in Scala. So what does the blocking molecule do? Well, the molecules we've seen so far are non-blocking. So when you emit them, there's a non-blocking side effect. It doesn't wait until any reaction starts. It just emits the molecule into the soup and you're done. Now, the blocking molecule emits the molecule and waits until a reaction consumes that molecule. At the same time, it's waiting until a reply. So the blocking molecule can extract a value from the reaction using the reply mechanism. So what is this reply? Well, reply is like a molecule that you emit from the reaction, but it doesn't go into the soup. It goes directly into the color. It unblocks the color.
Like data flow.
The question was, is this like data flow? So if you use blocking molecules, then you can synchronize everything. So you can synchronize every reaction. You can wait until first reaction starts, get its result, then start the second one. Yes, but this is typically not what you do. So typically you write a lot of non-blocking code, and then at some corner you wait. So that's similar here. And the syntax looks like this. So F is a blocking molecule, and it has two arguments in this pattern match. So this is a reply emitter, and you can use it to reply. Otherwise, F is just a molecule. It's just a way to write down this construction. So here's an example. Actually, let me show you the code right away, perhaps. So here's a test that so by the way, all these tests you can download. I have a link in the meetup page. In this test, we define the counter C, the decrement, and then we also declare how we are going to wait. So the point of this test is to count to 10,000. So we first have a counter that has 10,000 in it, and then we emit 10,000 decrement molecules. And we wait until the counter is 0. So how do we wait? Well, here's the chemistry. C reacts with decrement, and if X is positive, then we emit the other C. Otherwise, we emit nothing. Now, if we get C of 0, that gives you a special molecule called finished. And this molecule called finished reacts with a molecule called get, and that gives you the reply. So get is declared as a B, which is a blocking molecule. Everything else is an M, which is ordinary molecule. And so this chemistry works if you emit initial value for the counter, and then you emit 10,000 decrements, then we do get. So this actually blocks until get can be consumed. Get can only be consumed when finished is there. Finished is only there when C is 0. So that's how this chemistry works. Now, as you see, this is very easy to reason about. I'm just writing down what molecules I want, and I kind of obviously see what they will do. And that's fully concurrent. So I can have this decrement emitted from different threads, whatever. I can emit them from different reactions. I can do whatever I want. So let's run this. We'll see what happens. And then I see how much time has elapsed, just to find out how much overhead I have in this counting. problem. All right, so we have 500 milliseconds to count to 10,000. Let's count to 100,000. See what that is.
I guess the thread pool is somehow configured in there some way.
Right. Now, so I intentionally did not say the word thread so far. And when you program in the chemical machine, you do not use threads. So yes, in principle, you need a thread pool. The question was, where is the thread pool, right? Yes, there is a thread pool. You can have your own thread pools and provide them to each site. You can provide a thread pool if you want, or by default, there is a default thread pool. So I will not go into these details, but if you're interested, I can talk about this. I have thread management here with priorities and whatever. Thread pools are important for performance, but when you're just doing the logic, then you don't want to concentrate on that. You want to concentrate on the chemistry and plan it correctly. And once you have done it, then you can optimize. Let me go back to my slide. So this was this code. Another interesting thing is that we are embedding this paradigm of molecules and reactions into a functional language. And if you think about this paradigm, it's kind of neutral and orthogonal to all the other stuff in the functional language. It only does the concurrent part. Everything else you get for free if you are embedding it into a functional language. So for example, you get types, parameterized types. You can have whatever you want. You can have molecules with values that are very complicated. For instance, here is a function that defines new chemistry inside that scope. In the functional language, it's very important that things are locally scoped. So values that are in the local scope cannot escape. And that's important. And it's transparently used when you do chemical machine programming in Scala. So here's an example. I do the same counting thing that I did before, but the entire counter chemistry is inside a function. So this function returns two molecule emitters, one with unit, one with molecule emitter value. I can do that too. So this M is a type constructor for molecules, and the read, I'm going to, what is this? Yeah, the read that I'm defining here. See, this read is the argument, it is the value on the molecule get. So the molecule get is a value whose type is a molecule emitter. I can do that. It's fine. So what happens here is that inside this scope, I defined new molecules, C, Decr, and get. And then I define exactly the same chemistry as we saw in the test, where you decrement, and here you do another thing where the get is not blocking, but it emits a molecule read with the value X. All right, so this is a bit different, but that's okay. What happens here is that at some time we want to find out what the counter's value is. But this is non-blocking, so the result will come on a different molecule later. So that's different molecule is going to be a parameter. So here's how we use that. We say Decr and get is make counter, and then result is some molecule, and then we put that molecule onto the get and emit that, and later the result will be emitted. So now we can define some new chemistry using result. Now, why is this helpful? It's helpful because the counter is hidden. The molecule C is only available in this scope. There's no way for me to screw up this counter. I cannot myself emit a new molecule C with some new value. If I could, I would just screw up everything. This chemistry is based on the assumption that there will always be one copy of the counter in the soup. There will be one copy, and that will be the resolution of contention. If there are 5 copies, then all this decrement and increment business falls apart. How do you prevent people from emitting this thing? Well, you prevent them by putting it into a local scope. That's it. No amount of Java reflection will help you here. It's in a local scope, it's hidden. I have a test for this where I declare this function, and it does the same thing, except that now I have to wait a little, because this is now non-blocking. So just for the purpose of this test, I put a little sleep in here. Okay, so let me just run this to see that this works. Another example is MapReduce. Well, the future I'm just going to skip. This is really trivial. I'm just showing that if I have this paradigm, I don't need anything else. I can implement future. I can implement MapReduce, parallel MapReduce. I can implement anything else. I can implement actors. This paradigm is as powerful and as expressive as anything else. It's equally expressive to actors, let's say. So how do I implement MapReduce? Well, I have to formulate MapReduce in terms of chemical reactions. So what are the reactions? So obviously, map means that I'm splitting my computation into parts, and then each part does something. And I want that to be in parallel. Well, how do I do anything in parallel? Well, obviously, I need molecules with these values, and I need reaction, and the reaction will automatically run in parallel. I just declare it once, and it's running in parallel. Here's this reaction. This is the map. For the purpose of this example, I'm just multiplying by 2. So if I emit several instances, several copies of the molecule C, then this reaction will run in parallel, as many copies as my thread pool will allow. Transparently to the programmer, I just say, okay, I want to have sequence 1, 2, 3, and for each of them I emit a molecule C with that value. Immediately that gets done, the first reaction runs in parallel. The second reaction will accumulate the results in a list. So the res is the molecule that has a list value. And once it gets one of those results, it will accumulate the results. So this is going to be single-threaded, but that's just a reduce part. Reduce can be done multi-threaded, but it's more complicated. So I initially will emit the res with empty list, and then I get the result. So this is a third reaction which blocks until everything is done, and or actually no, it blocks not until everything is done. It's just an illustration. If I wanted to block only until everything is done, I'll put an if here on the length of this list. But I didn't do this for this example. So here's MapReduce. Yeah, here I put this if, and this reaction runs only when the list is full. So that's how easy it is. So I can run this, and let's see. All right, so 10,000 items will be 1 second. All right, well, there's obviously overhead here, but that's what we expected. All right, now let me show you dining philosophers. This is an implementation of dining philosophers. Basically, it's fully declarative. I define molecules T1 and so on to T5. They represent thinking philosophers, and H1 to H5 represent hungry philosophers. And so when the philosopher is thinking, then it thinks for a while, and then it becomes hungry. And then when the philosopher is hungry, it needs 2 forks, and then it eats for a while, and then it becomes thinking again and puts down the 2 forks. That's the chemistry that I'm writing down as fast as I can say it. And this is actually the code. I omitted declarations of all these molecules, but this is basically the code. Let me run this. Yeah, so they're eating, thinking. Right. Well, now let's look at Rosetta code. So what language would be good for this kind of problem? Well, actually, they have very, very interesting implementations in Prolog, in Haskell. Yes, they have all kinds of interesting. Let's look at Java. Well, I don't know what this does. It's not declarative. It's not obvious what it does. It waits, and then there's some token set, and whatever. Anyway, I think it's clear. Haskell's implementation uses software transactional memory, and so it's reasonably short. There are other things. So basically, what I'm trying to say here is that the chemical machine is declarative for this kind of concurrency. Message passing concurrency, no shared state concurrency, typically contention for resources, but no shared state. That's ideal. So I'm working on this, but what I think this paradigm would be good for is, let's say, distributed consensus, where you have message passing, would be more or less declarative. I haven't implemented it yet, but I'm thinking about doing this next. Paxos, exactly. Algorithms where you have message passing, and it's otherwise you have no shared state. So that is the domain for which this whole paradigm is a domain-specific language. Let me outline how you can think about the chemical machine or joint calculus as a development of the actor model. Imagine that I impose new requirements on actors. I want to improve the actor model, and I say, first of all, they have to automatically start. I shouldn't have to create actors and shepherd them when they die or whatever. I don't want to do any of this. I want to send them messages, and whenever I send messages, actors should start. If they haven't, whatever, I don't care. I don't want to think about it. I want to declare my actors and not imperatively create them and maintain their state or whatever. Second, I want actors to be able to wait atomically for a set of messages so that I have multiple dispatch, because actors can only wait on one message at a time. And I want them to have statically typed values, the messages, I mean. So, if I impose these requirements, first requirement immediately forces me to make actors stateless. Because if they are automatically started, there's nothing for me to, there's no state. I can start them whenever I want, and they must start with the same state somehow. So they must be stateless. User code will define computations, but it will not manage actor instances anymore. And the third thing that follows is that message emitters that were specific to actors, to actor instances in the actor model, they should not be so any longer. They should be specific to data. So here's an example. If I have two reactions, one consuming A and B, and another consuming B and C, and I emit B, and I emit A, obviously, B is not specific to any one of these reactions. The B is specific to the kind of data that I'm talking about. So I'm dealing with special labels on data that make data concurrent, rather than dealing with specific instances of processes that will compute with that data. So it becomes much more declarative. So I have multiple messages will be automatically parallelized. If I emit here B1, B2, B3, and if B could be consumed in multiple actors, they all start automatically. So my parallelization becomes automatic. And I need to create a blocking emitter because I have this blocking send construction. But this is, like I said, this is a detail that does not actually change the way we program. So here you see, if you compare left and right, here you see how you start with actors, then you want to make them a little better and easier to use, and you arrive at this. To summarize, what I'm going to do is I'm going to unseat akka. So from now on, you will stop using akka for your projects. Instead, you will start using this completely untested library because it's much better. I'm sure you see that this is so. Last example, if I have time. Do you have time? I have time. Last example is the merge sort algorithm. The merge sort algorithm is, in this implementation, automatically parallelized. So how do I do that? I need to start thinking in terms of molecules somehow. This is the only way to compute anything in this paradigm. So how do I think of merge sort algorithm in terms of a chemical reaction? Well, obviously, the array that was not sorted sits on some molecule, and then something happens, and then the array that is sorted gets emitted on another molecule. That's how it must be. So then, okay, what are the intermediate molecules between these? Well, let's start right here. So merge sort is a molecule, and let's say that sorted result is the molecule that will be emitted when the result is obtained. So this is like a continuation passing a little bit. But, okay, so this is the initial array. We split it into two parts. So suppose we have we have this function, right? Split at. So we split it into two parts. Now, what next? Well, we need to sort all of these. Somehow we need to sort the two parts and then merge the results. So how we do that is not clear, but the result must be emitted like that. Okay, well, so how do we do that? Well, we do that recursively. So the sorted must actually be the same as the merge sort somehow. So how do we do that? We emit two copies of merge sort with the two parts of the array, and we put sorted 1 and sorted 2 as the result molecules on these two merge sort molecules. So each of them will use that as a continuation. So it will emit them when it's done. And then we have a reaction here that will gather the results. So that's the idea. So we split, and then the splitted parts are on special molecules, sorted, which will be emitted when they are sorted. And then we declare two reactions, one inside another. The first reaction is this one, and the second one is declared inside. And that's actually it. So here's the full main part of the code without declarations that implements exactly what we do here. So there's one reaction which is outside. Then we check, the condition that the array is not length 1. And then we split it into two, and then we do exactly as I just showed. So here's the code. So I have array merge. I just implemented something that works, doesn't matter. And I define all of this in a function. So all of this, I have two sites now. One is for the final result that will be waiting for some blocking molecule. And another site for this nested stuff. All of this I want to be hidden from the user. So the user only calls this function, perform merge sort, and gets the result. I don't want the user to worry about these molecules. And by the way, this is actual recursive chemistry. So each molecule defines a new reaction, which again defines a new reaction, and so on. So this is a tree of computation that is created at runtime, even though all of this is statically defined. So there's no runtime definition of new molecules, of new reactions. There's no modification of anything. Everything is static. And yet, recursion, just for free, gives us this power. So let me see.
So are your sites then recursively?
This will be a new site every time.
Yeah, new site each.
Yeah.
Two
Because it's in the scope of a function, right? So each time you call this function, it's a new site. And new molecules. So this is going to be a new molecule each time. And all of them are going to be hidden and completely transparent. So there's no way that one branch of this tree is somehow interfering with another branch. These molecules can never react. So you see, I define this reaction, sorted 1 plus sorted 2 equals sorted result. But there will be many molecules called sorted 1 in different parts of the tree. They will never react with each other unless they're in the right part of the tree. Because that's all declared in local scope. So functional programming, recursive functions and local scopes gives us this for free.
Lives on the stack.
Say it again?
Most of this lives on the stack.
So the stack, actually, no, none of this lives on the stack. It's all in a heap. It's all in a heap. There's no function calls that call each other. This is not a function call. This is an emission, which is non-blocking. You see, none of this is blocking. So this sorting is completely non-blocking, completely concurrent, and none of this actually lives on the stack. So there will be no stack overflows. So it's all, because reactions are not function calls. Reactions are magic, right? So they're, you need to download this library. You will see with your own eyes.
Weaknesses or features is that in this traditional Scala implementation features they can't be canceled. Can you cancel a computation here?
So not at this level. You have to implement cancellation yourself. What you can do is you can kill the entire reaction site if you want. That's kind of a brutal way of canceling computations, but you can do it. So yeah, the question was, can you cancel some of these computations? Well, actually, no. You could here implement. So the way to prevent things from running is to withhold molecules that are necessary. So if you have a reaction that requires molecules A, B, and C, and you don't give A, this reaction will never run. So if you want to cancel something, don't give it A or B or something. Make a molecule that will be emitted when you want it to run and will not be emitted when you want it to cancel. That's the basic way. Or else you need to do other things. You need, in the body of the reaction, you need to check if it hasn't been canceled or something like this. You can implement that. At the basic level, it is not available. So, okay. It's a little table. I'm almost out of time, so I'm just thinking, what is, yeah, I mentioned the Wikipedia page, right? Now, they have a very different terminology with messages, channels, processes, which I find confusing. But this is a dictionary that tells you what that terminology means. There are other implementations of joint calculus. There are quite a few. And actually, Martin Odersky was the first one in this list who implemented joint calculus as a special new language called funnel. And this language didn't go anywhere for some reason. And actually, I never got an answer as to why people like Philip Halle, who is a central contributor to Scala, worked on joint calculus. He made an implementation. None of this ever made into standard libraries. Another implementation by Hu Jianxin, who was building upon Philip Halle's work. I'm building upon their work as well. none of this is ready for use, actually. So I'm trying to make a library that is practical, is not just an academic exercise, a library where you can implement things, test things, that you can control your performance, that you can control your threads. For example, if you are programming on an Android device, you need to control which thread is the main thread and which is not the main thread. And you cannot put computations, long computations on the main thread, because that will kill your UI. So you need to have that kind of control. So then if you want to use this paradigm, the chemical machine, then you have to tell the chemical machine that these reactions cannot run on the main thread, but this reaction must run on the main thread, and so on. So this kind of thread control can be implemented. There are all kinds of things that are necessary to make this industry ready. Some things, for example, that are necessary is good documentation and examples. So I'm writing a tutorial and hoping to get people to understand this thing. Okay, I'm done. So hopefully you understood that this completely blows out of the water everything else. You know, threads, you don't want to touch threads anymore. Now you only want to think in terms of molecules from now on. If you're interested, you can go to my repository. There are examples. There's a Hello World project that you can download, tutorial, and my talk slides as well. So thank you very much. All right. Questions, please.
So it seems like this could be, I mean, there's nothing that you can, what you described that precludes it from being distributed potentially across multiple machines, clusters, whatever. Are there any practical word to that effect?
Yeah. So the question is, do we have a practical implementation of distributed chemical machine or cluster or multi-processing, multi-cluster chemical machine? This is not yet implemented. Now, there are questions about how to do this in the best way. So there's one way of doing it, which is kind of straightforward, which is that each node declares some molecules, and you can inject them into the node remotely. So this is remote molecules. So I know that this molecule is destined for this HTTP URL and only for that. And that HTTP URL promises to know what to do with this molecule, but I don't. So that kind of thing can be done. I'm not sure this is a very elegant design, but this can be done as a first step. A second thing would be to fully share the chemistry between clusters. Between nodes in the cluster. And that is hard. That actually requires consensus algorithms as to who has consumed a molecule, right? Which node has already started or not yet already started, or maybe started but then crashed or something. So that kind of thing is not so easy, but I'm thinking about it. I don't think there is a good description in the literature about how to do that. I haven't seen it. So the academic papers don't discuss that. They talk about other ways. So, but basically that is something that needs to be done if I want to use this in a distributed setting. Yes, please.
Two questions, if I have time. But the first is, this seems to be like a push-based model where you basically throw molecules onto this queue. And so the question that comes to mind whenever I see push-based models, what's the back pressure?
So the question is, this is a push-based model where I throw molecules to the queue. What is the back pressure? So back pressure needs to be implemented in some way. It is not yet implemented in my library. So one way of doing this is to have static analysis. I know where these molecules come from. So I know which reactions, at compile time, I know which reactions are declared. So I can, or very early at runtime, I can analyze that. Then I can tell that reaction not to run if the consumer is backed up. But that's one thing that I'm thinking of doing that. But the second question?
So the second question was, you mentioned that Go is a macro, and I was curious, like, what exactly is it doing, and what necessitates it being a macro?
Okay, so it used to be not a macro, but then I could not implement arbitrary partial functions. So what the question is, why is Go a macro? What does it do? So it looks at this code. It actually currently doesn't do anything with this code. This code runs as it is. The Go macro looks at what molecules are inputs, what molecules are outputs. Like this is the output, this is the input. And it makes the scheduler code so that I know what reactions consume what molecules. Partial functions are opaque, so I need to inspect their code. It turned out to be very difficult without a macro to figure out what is on the left-hand side of a partial function. I tried it, the first versions did not use macro, and then I found that I could not have unrestricted patterns here. There were some weird restrictions on the patterns that anyway, so the macro mostly does static analysis. For example, I can detect live lock. A live lock is a compile time error. Let me see if this actually works. Maybe I'm going to risk this. Okay, I'm going to add a reaction here with something like, okay, I'm going to add another molecule. All right. So I'm going to say A goes to A. All right. Looks okay, right? Just chemistry. So A goes to A. What will happen if I run this? I hope it's going to tell me. Now, look at that error. Unconditional live lock. Input molecules must not be a subset of output molecules with all trivial matches for A. So it tells me that this is meaningless. This is useless. If I had some value here and then some condition, that could have been useful. But as written, it's completely useless. So this is a macro that does this analysis and gives me this error. Sorry. You had a question. Right. So the question is there any advice for converting usual code, like barriers or imperative concurrent code, into the chemical paradigm? Yes. So that is the volume of the tutorial that I'm writing. I'm going through many examples, such as rendezvous, barriers, all kinds of typical problems of concurrency that people have, and show how to reason about them using the chemical machine. So if you read that, there's an interesting book online which is called The Little Book of Semaphores, which implements a lot of concurrency problems in Python using imperative code with semaphores. I'm going through that book. I plan to do everything in that book using the chemical machine, and to show the reasoning also, not just give the solution, but to show how you arrive at the solution, how to reason. So reasoning about code, that's what I want to understand. Is it actually easier to reason about concurrency or not? And to understand that, I want to go through. So I'm halfway kind of there. You can see all the barriers are already implemented. Rendezvous is implemented. So that's how it is. Yes.
So
am I right that the sort of key to your downing philosopher's solution is that your pattern matches are consuming all those inputs atomically, right? So your hunger and your two appropriate forks are all getting consumed.
So yes, so the question is that in the dining philosopher's solution, the input molecules must be consumed atomically or else it won't work, precisely. So the operational semantics of the chemical machine guarantees that. So for example, here there is a contention. F12 can be consumed by first reaction or by the second reaction. So there is a contention of two reactions to consume one and the same molecule. And we force this contention, we only emit one copy of that molecule. If we emitted several copies of it, it won't be a problem. But we only emit one copy of F12. So there is a contention. The chemical machine does not tell you how it will choose, but so that is not deterministic. But it is guaranteed that all the input molecules are consumed atomically, concurrent with all other reactions that are trying to do the same.
So it's really your implementation that's solving the dynamic philosophy problem, right? I mean, there's no algorithm there.
No.
Yeah, that's similar to this question about when you have contention, which is the reactions are not associated, which is the order of which reaction happens might affect different results.
Right.
And
So
usually, one operation and then what tools I can have to interpret the orders.
So the question is, if I have contention, what tools do I have to influence the order in which reaction will actually start? So this is a very good question. And at the basic level of the chemical machine, there is no way of influencing the order of reactions, period. So there is full non-determinism as to whether the reaction will start now, later, or at any time. It is not guaranteed that the reaction that I declare first will be run first, or anything like that. This forces the programmer to rethink the concurrency, to make it so that the order is enforced explicitly, and not just because some rule is declared with higher priority. There are no priorities, there are no tools to say one molecule has higher priority than another molecule, or one reaction than another reaction. If actually, I would make even the argument that it is better to have no such tools than to have them, because if you have priority, then you get an illusion of control. You actually don't get control, but you get an illusion of control. You're just setting yourself up for more race conditions later. Sometimes the reaction will happen according to your priorities. At other times, because molecules are emitted concurrently at unpredictable times, the other reaction will start first. And instead of giving you a tool that doesn't work reliably and gives you an illusion of control, the chemical machine gives you no such tools, but you can always do what you want by defining more molecules. And remember, the only way to prevent a chemical reaction from happening is not to give the reagent into the solution. Once you give it there, you have no control. So the primary means of control is withholding the inputs, making sure that the input is emitted at only when the data is actually available. So think about it as data for computation. When data is available for computation, there's no reason not to do the computation. So ordering the computations should not be important. The results should be important. So that is the paradigm. And getting used to it takes maybe some time, but I find it very refreshing. Thank you.
So in this code, philosopher 5 could get scarred, right? It just might never go, right? How would you?
The question is, this code does not prevent starvation in terms of philosopher, let's say philosopher 5 never getting to eat. How would I prevent that? So yes, if you want to guarantee, so this code does not guarantee that the wait time is bounded, for instance. It could be just by bad luck that both of your neighbors keep getting hungry and you never get your fork. So that cannot be prevented. Now, how would you prevent that? By putting in some more molecules. So you need to get more into this data. For example, each philosopher will carry a value that says how long it's been waiting. And then I can have another molecule that decides whom to give the fork. Give the fork to the left or to the right. And then you compare how long they've been waiting, and you give to the one who's been waiting longer. So you get many more reactions, maybe, but maybe twice as many. But that's how you would do it.
Is this work applicable to any problems you're working at?
The question is, if I'm using this at Workday, no, not at the moment. So I would actually comment on this. When do you need to use this kind of thing, right? I mean, apart from having fun, the answer is you need this kind of concurrency framework when you're implementing a very complex system, a very complex concurrent computation, such as, let's say, a consensus algorithm. So if I want to re-implement Zookeeper, I would use this. Because I want to have declarative unrestricted concurrency. At Workday, we do not need to implement such things. At least we haven't had that need. So for example, an ETL pipeline or a streaming pipeline does not require this power. This is too much power for, if you have a streaming pipeline, you consume data from Kafka, and you go through some computations and you emit the results to database, whatever. You need a streaming framework. You don't need an unrestricted arbitrary concurrency framework. It would be actually counterproductive to do that. You can implement it like this. It will be more complex. You'll be debugging longer. You should use something like Akka streaming. If your problem can be solved with parallel collections or Spark, that's exactly what you should be doing. You should not be trying to do actors or arbitrary complicated concurrency to do that. You should use a formalism that's least powerful, sufficient to solve your problem. So right now, we might be, maybe 6 months from now, we might want to implement a job scheduler. Now that's something that might be interesting, because job scheduler requires to monitor things, to react to things at arbitrary order. Maybe that's when we need that. Right now we don't. So I also want you to think about when you need power and how much power you need. Sorry, there have been somebody had a question. Sorry. Okay, I don't know.
I did have one.
Okay.
If you were writing that streaming, implementing that streaming library, would you use this?
Yes. So if you want to implement Spark yourself, if you want to implement Akka streaming yourself, yes, that's when you need higher concurrency power.
Coming off of one question, you did mention job scheduler, so could you use this to implement an air traffic controller system?
Yes.
Really?
Well, you can use this to implement anything, but
reliably and accurately.
sorry.
Is your joint calculus free?
Yeah. So the question is it Turing complete, and can I implement a reliable air control traffic system? Yes, it is Turing complete. You can implement lambda calculus with it if you want to make sure. Air traffic control system is something I'm not extremely familiar with. What are the requirements? Is it hard real time? Is it because if you're nodding to my question, then I must say this is not hard real time here. We are unfortunately we cannot give any guarantees here as to when any reaction will start. There are no tools to guarantee that. we can try to optimize, and that's not enough, perhaps. So hard real-time problems are too hard.
Why do you?
Sorry.
So maybe you like these people's first one.
Yeah, let's...
So currently is the default setup that it uses all available processors. So if I had an 8-core system, it would use all if they were available.
Yeah, so the question is, will it use all cores on a system, as many as available? Yes, so by default, all sites are running on a thread pool that uses all cores. Now you can change that, and there are some situations when you want certain reactions to run on fewer threads, and let's say higher priority threads, and so on, and you can do all that. Yes.
But it seems like you should be able to dynamically pivot or temporarily disable certain reactions that use guards. So you sort of simulate like a dynamic systems or like forces.
So the question is, can I use guards to simulate dynamically changing systems? Reactions that are not statically defined. Did I understand that right? Reactions that are not statically defined but that change with time.
Reaction range.
So, okay, I would say to some extent you can do dynamic things, but all the possible reactions must be declared statically. However, you can add instances. For example, how would I define the code for n philosophers instead of 5, where n is a runtime parameter? I can do that. I can declare an array of molecules, an array of reactions, and then I can dynamically construct the site at runtime. So this is dynamic, and yet every reaction is statically defined. So there must be this static guarantee, and yet you can add reactions at runtime. But those reactions, another example is the merge sort. In the merge sort case, I only defined 2 reactions statically, but actually, depending on the size of my array, it could be quite a large tree with different reactions. Your question.
What do you think of the perspective that all of these joint calculus and other accurate model are attempts to paper over the fundamental reality that von Neumann architecture sucks and we spend 90% of our time waiting on data from us, and you will never be able to get an elegant or clean concurrent/parallel computation, period, because you end up just shifting around complexity between.
Sounds like you want to program DSPs.
And sorry, DSPs?
Yeah, they're not one.
Yes, I do. And then in but essentially, so basically my question is, why do you think this will help versus the actor modeling? And why do you prefer this to data flow? Is it an instinct? Did you
Okay, so
a specific paper that you're like, this is real cool?
So the question is, why would I prefer chemical machine programming to other paradigms, given that none of this removes the suckiness of the von Neumann? We're stuck with that at the moment. In most places, we have to use that architecture. So the question is, how do we use it the best way? The best way is to do declarative programming. You find your domain and you do declarative programming in that domain. That's the most efficient way of programming. Now, in my view, actors are not sufficiently declarative. You have to do a lot of bookkeeping in order to use them. Now, chemical machine improves upon actors and removes some of that bookkeeping. That's it is not just because I like it, but it's because it actually allows me to think faster about concurrency and write less code. Does it resolve all difficulties? Of course not. Yes.
So, it's a known fact that pi calculus is strictly stronger than actors model, because one can model another, but not So not being familiar with joint calculus, I wonder where, well, that was like a hierarchy of two. So where would you place joint calculus in this one?
Okay, so the question is, given that pi calculus is strictly stronger than actor model, where do I place joint calculus in this hierarchy? I don't want to pretend that I know. Now, what I would like to say that is my intuition for this is that for real-world problems, they are of the same power. Maybe there is something that you cannot express, which is easily done in different ways. So for real-world problems, actors are as powerful as you need, and joint calculus is similarly as powerful as you need. So they're, in my view, I would say they're the same. But in my view, pi calculus is included in joint calculus because you can do you just say, well, your reaction cannot have two molecules and have one molecule in the input and then something in the output. Your channels can be passed as values on molecules. In my view, pi calculus is the same in power in joint calculus, but like I said, I might be mistaken here. And I didn't want to show things that are too theoretical, but feel free to ask me after the talk.
If you're doing a concurrent counter along the lines of what you showed, then if you want to sample it, asynchronously as well, it seems like you can never kind of know that you're getting the current sort of sum because your question might be beating out your increment decrement. Is that right?
So yeah, the question is, when I do the concurrent counter in this way, then I'm getting the value out of it, and the getting of the value interferes with increments and decrements. So I cannot guarantee that I get the current value. Correct. And actually, this reminds you that you actually can't guarantee that at all in any way. There's no way to guarantee. You don't know when things are going to be incremented. This is just in your face. You thought that you could, maybe, when you wrote Java. That was a mistake.
Well, if you have one mutex around your counter, everything's
That's true. That's true, but you don't know when these people are incrementing your counter. I have a mutex here. The atomic nature of molecules, that they are consumed atomically, guarantees me that I have a mutex. Either the counter is being updated or I can read it, but not both. However, I don't know when things are being updated, and I cannot guarantee anything. So this is kind of in your face. It tells you that you can't guarantee that. Please design your program so that you don't depend on this. Because if you do depend on this, you're setting yourself up for a race condition. So this kind of paradigm forces you to confront these things. So yes, you cannot know. For instance, I throw in 1,000 increment molecules, and they're being processed. I have no idea when they're finished, and that's how it is. That's how concurrency works.
Well, if you're doing some different model and you're all your increments and decrements, you can know that your question is being processed after all of the increments and decrements that came before your question.
That's only when you. Okay, so the question is, if you emit a lot of increments and decrements and you emit the question, then you know in which order you have emitted them. So that if you only emit them from one thread, yes. But if you allow other threads to emit, you have no idea in which order anything comes. So yes, I have a feature, I did not show it, which is called ordered molecules, where the emission order is preserved, and that is automatic. So you don't have to declare them ordered. Whenever the chemistry is such that the molecule is ordered, that is statically determined, and it is being treated as such. So yes, in that case, you can do that. But if this molecule is being emitted from different reactions, from different threads, you have no control over that anyway. So the programmer has to design the chemistry in such a way as to not to depend on this. And that's the only way, and it's in your face here. So that's actually, in my view, very helpful. Okay.
Have you thought about what would happen if you allowed tests for like the absence of molecules?
Yeah. Question: can I implement a test for absence of molecule? No. I don't want to repeat myself, but this test will be a self-delusion. There's no way to determine that a molecule is not there because you don't know when it is not there.
Well, at any particular time.
At any particular time, what you can do is you can set a timeout for something to happen. That's what you can do. So you can say some computation should have started within this timeout and given me a result. And if it didn't happen, then maybe that molecule wasn't there during this time. But you don't really know if that's even true. Maybe the molecule is there, but your CPUs are all backed up, processing some jobs, and you have no idea when they're going to be done, so there's no control. So you see, no, you cannot have a test for anything that, you don't have this idea of things happening right now and checking that. You don't have this. You're in this world where time is fluid and you can wait for something to happen, maybe. So it's a very different kind of model. So no, you cannot test for absence.
Yeah, detecting the absence of something is local, it can't be global.
Yes. So your comment was that absence is local and not global. Time local. Absence is time local. Yes. Leslie Lamport, I think, talked about this in one of his papers. That you have this relativity of time, and you have something.
Probably into TLA plus shell, right?
All right. So thank you very much.